Monsieur l'ambassadeur, monsieur le président de l'Académie des sciences, monsieur le représentant du ministère, monsieur et mesdames les représentants de l'ambassade des Pays-Bas en France et de France aux Pays-Bas, chers amis, chers collègues, je vous remercie d'être ici. Bonsoir à tous. Je souhaite d'abord commencer ce petit discours en remerciant très chaleureusement l'Académie des sciences et l'Académie royale hollandaise pour m'avoir remis ce prix Descartes-Huygens 2017. C'était un très grand honneur pour moi, vraiment merci beaucoup. I think I will switch to English. I think I was instructed to give my lecture in English. So in the next few minutes, I want to take you into a journey through the oxide world. This is my field of research, and I want to give you a brief introduction to this field. So I want to start this presentation by showing you this picture of our planet, and I want to point out that the crust of the Earth is almost entirely made of oxides. Oxide of silicon, aluminum oxide, iron oxide, magnesium oxide, so really oxides are everywhere, and therefore it's not a surprise that they are important materials. So the oxide that we investigate in our group are of a special structural family called the perovskites. And you can see here a picture of these perovskites, and their formula is shown here, AbO3. So you have three oxygens. The oxygens are grouped to form an octahedral cage. The B element is at the center of this cage, and then here you have this green atom, which is the A atom. And so what is really remarkable about the perovskites is that you can fit almost all the elements of the periodic table into this structure. So for the B atoms, for instance, you can choose almost any of these transition metal elements. So you see, for instance, iron, manganese, titanium. And for the A ion, the green atoms, you have a choice of all the rare earths and also these elements called alkaline earth. So most of the properties of the perovskites are determined by the atom at the B side, so the titanium, iron, manganese, and the atom at the A side are, depending on their size, are going to modify the structure, and you can see that this will provoke some rotation of this octahedra, and this will tune the properties. So because in this perovskite structure it is possible to accommodate so many different elements, they exhibit a very broad range of physical properties. For instance, you can find insulators, so materials that don't conduct electricity at all, metals, so good electrical conductors, superconductors, perfect electrical conductors at low temperature, and also magnetic materials and ferroelectrics. I will show you in a minute what a ferroelectric is. And what's remarkable is that they all exist in the same structure. So very similar, but in fact different in their properties. So I want now to explain a little bit the properties of the electrons. So we work with electrons all day long. That's really our subject of investigation. We try to understand what electrons, how they behave in these oxides. So the electrons, of course, have a charge, the elementary electrical charge, but they also have an important property, which is called the spin. That corresponds in a simple picture to the rotation of the electron around itself. So you can rotate clockwise or counterclockwise, and this corresponds to what we call a spin up or a spin down. And the spin of these electrons, which is a little bit like a very small magnet, can be ordered in matter. So they can be aligned parallel to each other, as shown here, and this is what we call a ferromagnetic material, ferromagnetic state. So similarly, there are other orders in the materials, in condensed matter. For instance, you can also have what we call a dipole order. So here you have an order between positive and negative charges, also aligned parallel to each other in the material. This is what we call a ferroelectric state. And there are other orders. One is, for instance, the so-called charge order, where here you have small amount of electron, big amount of electron, again aligned with each other in the material. And this is a correlated state. So what's interesting is that you can manipulate these states by applying an external stimulus. For instance, if you apply a magnetic field, you can manipulate, you can switch the direction of all these spins. Taken together, we call them the magnetization. And so we can reverse the magnetization by applying a magnetic field. Equivalently, for the ferroelectrics, all these dipoles together, they are called the polarization. And we can reverse the polarization by applying an electric field. And this charge order, if we apply light, for instance, we can destroy it. So we can control this charge order by light. So what's remarkable also is that these orders have some kind of a memory effect. So if you apply a magnet to one of these ferromagnetic states, if you apply a magnetic field, you remove the magnetic field, the magnet will stay as it was when you were applying the magnetic field. So there is a memory effect in the ferromagnet, in the ferroelectrics, etc. And so these materials are used to store information. And for instance, the disk drives in the computers use ferromagnets to store binary information, 0 and 1s, as you know. So they store information. They need to be manipulated by magnetic field, electric field. You need to be able to read the information, the 0 and the 1. And you need to convert this information into an electrical signal because in the end, everything has to be an electrical signal, a voltage. So this is the kind of situation that we are trying to address and understand with our oxide materials. So before giving a few examples of these results, I want to show you briefly how we make these materials. So we use a technique called pulse laser deposition, PLD, and this is a picture of one of our growth systems that we have in our lab in Palaiseau. So, all these chambers work in vacuums. We have pumps everywhere to have a very good vacuum. And I want to use this illustration from my colleague from Twente, who are really expert of this technique PLD, that shows you a little bit of this works. So this is a sketch of this vacuum chamber. We have a laser, very powerful laser, which is here. And then through different mirrors, we can send the laser beam into the chamber through a window, which is not shown here. And this laser beam is going to hit what we call the target. That's a small pellet, like the size of a coin, if you want. But it's not made of metal, it's made of a ceramic. And it is actually containing all the elements which we want to have in the thin film, which we are going to deposit. So in front of the target, we have a small piece of crystal, which we call the substrate. And we are going to deposit a very thin layer of the material of the target, layer by layer. So atomic layer by atomic layer. So I have a small animation for you to understand this a little bit better. So this is again from my colleagues from Twente. So you see that the laser is coming, hitting the target, and this kind of evaporates the material, which is then deposited on the substrate. And so we can hit the blue material, we can hit the pink material, so we can grow only a film of the blue, only a film of the pink, but also multi-layers by alternating deposition of the blue and the pink. And in the end, this is what we get, what they get. Actually, this is a picture again from the colleagues from Twente. And you see this picture, this is not like a nice curtain or like a nice piece of cloth that you would have in your house. This is actually a transmission electron microscopy image of one of these samples, one of these multi-layers. And if you zoom in, you see that the white regions correspond to one material, for instance, the blue material before, and here the dark correspond to the pink materials. And they show with brighter or darker contrast because they are different elements that respond differently to the microscope. And each of these small dots is actually a column of single atoms, okay? For instance, a lanthanum atom, titanium atom. So it gives you a flavor of the control that can be achieved to grow these quantum materials. So now I want to give you a few examples of some experiments that we have done in our lab in different perovskites that we grow by the same technique. The first one is with this material which we call bismuth ferrite. So it has oxygen 3, of course, and then bismuth and iron. So it is a material that is at the same time ferroelectric, so it has these ordered dipoles, as I showed you. And at the same time, it is magnetic. So this is very rare to have this coexistence, and we call these materials multiferroic. So here the magnetic order is not the simple ferromagnetic with parallel spins. It's more complicated. It has a spiral order. Okay? And so because we have an electrical order and a magnetic order in the same materials, there will be a coupling between the two. And so we are going to be able to control the magnetism, not by a magnetic field, but by an electric field, which is much better in terms of practicality and low power. So this is an image of our sample. The yellow and brown region here corresponds to a region where the polarization of the ferroelectric is along different directions. So this is a bit complicated. So we use a very sharp tip to apply an electrical voltage and then induce the presence of just one single domain region. So here we have a region where the polarization is homogeneous, say here along the left. And then we want to see what happens to the magnetism in that region. So we use a different microscope. And this is a collaboration with a group in Montpellier. And we are able to get this kind of picture that shows this nice red and blue stripe contrast, which is the indication of this cycloidal order that here has a well-defined orientation. And now if we come back to the sample and we apply an electric field in the opposite direction, we can reverse the polarization direction, and you can see that the direction of the stripe is changing by 90 degrees as well. So we are able to control the direction of this magnetic cycloid by an electric field. We control magnetism by electric field. This is much more convenient than to do it with a magnetic field. So another example is now a charge order material. This is a nickel perovskite. So we have here, for instance, neodymium nickel oxide. And one particularity of this material is that they are very insulating at low temperature and very good metals at room temperature. And there is a very sharp transition between the two states. You see, so that's the resistance as a function of the temperature, very high value at low temperature. This is 50 Kelvin, so more than 200 degrees below minus 200 degrees Celsius. And at room temperature, here you have a low resistance, that's a metal. And so in collaboration again with the colleagues in Twente, we are able to tune this transition to have it just at room temperature, 300 Kelvin. And now we are going to use light to manipulate the resistance state. And so this is a curve taken with the light off, and this is with the light on. And you see that we have a very strong decrease of the resistance at room temperature. So we have some kind of switch of resistance which we activate by the light. And this is maybe easier to see here. When we apply a pulse of light, the resistance decreases by a factor of 2 or 3. Another example that I want to show you, it was mentioned briefly in the introduction. It's these devices which we call ferroelectric tunnel junctions. So we have, again, the same material that I showed before, bismuth iron oxide. Very thin layers, just a few atomic layers. And here what we are going to do, we are going to apply a current perpendicular to the layer. And the resistance of the material, as we discovered, is extremely sensitive on the direction of the electric dipoles of the ferroelectric bismuth iron oxide. So when the polarization is pointing up, we have a very low resistance. When it's pointing down, we have a very high resistance. And what's even more remarkable is that we have all intermediate states of resistance which correspond to situations where we have a mixture of domain with the polarization pointing up and pointing down. This corresponds to the gray and dark contrast here. And this qualifies these devices as memristors. And these memristors are electronic analogs of the synapses in our brain. And they are, of course, very important new devices for the development of new chips that would operate mimicking the way the brain works. So you can combine electrical neurons with electrical synapse and build a chip that would be an electronic analog of the brains to have very efficient computing. And I want to mention that the project with my colleague Beatrice Noeda in Groningen will be revolving around those ideas, but with new approaches, new concepts, again, using the material bismuth iron oxide. And finally, I want to close by showing this remarkable example in my mind. That is the combination of two materials, lanthanum aluminum oxide, strontium titanium oxides. So these are two insulating materials, transparent, they are completely insulating like a piece of glass, a piece of wood. And what is really remarkable is that when you put one on top of the other, you have a very good metal at the interface. So this is really incredible. It's like if you take two pieces of bread, and like by magic, you have a piece of ham appearing in between. So this is an image, again, of one of those samples. And we investigated those materials for a few years. We demonstrated that they have this very low resistance just at the interface. And now we are combining them with ferromagnetic materials because we have discovered that they can very efficiently convert a spin current, so current of spins, into a charge current. So they are very efficient to read, if you want, the magnetic information. So efficient that the company Intel is very interested in these results for the new transistor that they have proposed to replace conventional so-called CMOS transistor, which we have now in all our phones and computers. And so now you have this logo on your computer, but maybe in a few years we have this one. That's what we hope, actually. So this is the end. I want to end by thanking all the people who have been working with me, in particular my colleague Agnès Barthélémy, who is here with us, and Albert Fert, and all the people who are in the lab, and all the students and postdocs that made this work possible, and all the collaborations in France and abroad. Thank you very much.